Hello everyone, my name is Mingxuan Li, an undergraduate researcher at BUPT and Queen Mary University of London. Today I'm very excited to share our latest work on challenging that affects of almost every school and university, the university course timetabling problem. And this is our team, and I'm the second author of this paper. So while we live in an era of advanced AI, it might surprise you that many universities around the world still heavily on manual scheduling or old, outdated software to organize their classes. The main problem here is that every single school has its own social needs, from different campus layout and faculty preferences to complex degree rules. It is nearly impossible to create a one-size-fits-all solution. All of these different, often conflicting rules end up turning course scheduling into a very complex real-world puzzle. So to bridge this gap between the theoretical research and these complex real-world needs, the International Timetabling Competition, known as ITC 2019, introduced an excellent benchmark. To fully understand this challenge, we need to look at it from two connected parts. Firstly, from the classroom perspective, every single class must be assigned to a specific time and a specific room. So, and second, from the student perspective, the individual student must be sectioned into these scheduled classes to maximize the efficiency. Combine these tasks is give us the university course timetabling with student sectioning problem, which form the exact foundation of ITC 2019 benchmark. So in this complex environment, constraints are strictly divided into hard and soft constraints, while the soft constraints define the overall quality of a timetable. And satisfying all hard constraints is a must-have condition to achieve feasibility. So to evaluate these solutions, the official ITT 2019 benchmark consider four different types of constraint: time, room, distribution, and students. Each of these with its own penalty score. The official validator then calculate a total cost based on these penalties. However, this official code measure has a major flaw. It only gives a useful score for valid, fully feasible solution because it fails to give a fair penalty for bad assignment during the early stage of optimization. It provides poor guidance for search method trying to move forward feasibility. In short, it leaves the algorithm blind when it is searching through the invisible solutions. So how do we efficiently break through this wall and find a feasible solution? The key is to unlocking this problem is to split it up. You make the huge search space much smaller. We put aside the student sectioning subproblem for a moment and focus heavily on the core course timetabling subproblem, the UCTP. By solving the UCTP first, we can build a solid foundation to guide our search directly toward feasibility. So to effectively guide our algorithm, we first had to rethink how we evaluate a timetable mathematically. We built this up to three simple steps. Step one and two are about setting the ground rules. Before we look at the whole picture, we must define what makes a single class assignment accessible. As shown in the first two equations, a class is considered scheduled if it is simply given a time and, if necessary, a room. But just being scheduled isn't enough. We expand this into the definition of valid assignment. A placement is only valid if the time slot is actually open for that specific class and the room has the right capacity, and there are absolutely no clash between unavailable times. And this gives us a strict yes or no baseline for every single class. So within the strict baseline set, we introduce our co-contribution in the third equation, the distance to feasibility or DF matrix. Instead of getting discredited by minor soft constraint, this equation calculates a clear continuous penalty. We sum up three major mistakes. Every class that fails our valid assignment check, every rule that suffers from overlapping classes, and every violated hard constraint. So by summing this up, the DF matrix tells the algorithm exactly how broken the timetable is, providing a clear path to follow. And this mathematical foundation brings us to the major breakthrough of our work, the two-stage approach. Because the DF matrix is so effective at fixing major conflicts, we split the optimization process into two parts. So in stage one, we completely ignore the standard cost matrix. The algorithm only mission is to minimizing the DF to zero, meaning we focus entirely on searching for feasible solution. And once and only once feasibility is achieved, we transition into stage two. Here, the algorithm switch gears to focus on quality optimization, using the official total code to improve the schedule and satisfy student preferences and solve constraints. In short, we don't try to solve everything at once. We secure feasibility first using our target matrix and optimize our quality second. So to test how well our proposed DF matrix really works, we choose two baseline metaheuristics that represent two offset ends of optimization method. Random search for pure exploration and hill climbing for pure exploitation. By selecting these two baselines, we aim to find out which search method, exploration or exploitation, is more important for breaking through the massive constraint of the ITC 2019 dataset. So when we look at the overall result across all 30 problem instances, the difference is very clear. Hill climbing perform much better than the random search in every case. Most importantly, only hill climbing successfully find fully feasible solution in the multiple complex instances, whereas random searches fail to achieve feasibility even once within the given time limit. As the final DF values generated by hill climbing were always much lower than those random search. So to understand why this happened, let's look at the convergence dynamic showing in this chart. So as you can see, hill climbing draws very fast at very start. It focuses on exploitation help it fix immediate conflict quickly. However, it also flatten out quickly because it's very likely to get trapped in local optima. So in constraint, a random search shows a slow, steady drop throughout the entire process, while its exploratory nature keeps it moving. It has a really hard time reaching the very low DF goals needed for a valid timetable. So in conclusion, our study clearly shows that higher exploitation is much more helpful for driving complex timetable problem toward initial feasibility. So building directly of these findings, our latest ongoing research introduced a new restart strategy that nicely balance the exploration, exploitation, uh, and to overcome those local optima for the hill climbing. This upcoming work will be presented in the PATAT conference, and we will publish a full presentation video for it very soon. And as an undergraduate researcher, deeply passionate about combinational optimization and operations research. I always welcome feedback, so please feel free to leave your comment or question below. If you are interested in our research or if you are looking to collaborate on future optimization and scheduling problems, please visit my website or send me an email. So thank you so much for your time, and I look forward to connecting with you.